All right, so here we go. So I can teach you how an air conditioner works by using 5 or maybe 6 water bottles. So some of you all, when I ask you questions and I said, how does an air conditioner work? How does it do what it's doing? How does it make your house cold? I get answers like it produces cool air, or it produces cold, or it, a lot of other fancy words that people throw around and they don't really understand it. It doesn't take long to even find a whole lot of people in this field that do this for a living. And when you start understanding what you really understand about it and you hear what they say, you realize that even though they kind of sound smart, they're pretty much full of it. They don't understand half what they're claiming to know. So I don't want you to be one of those people. I don't want you to be a know-it-all, but I also don't want you to be unprepared. So I can show you how it works just by this. So in your heat transfer modules, you went through and you learned how heat travels. So how does heat travel? Temperature-wise, anybody remember that, or did anybody catch that? It travels from a place that is warmer to a place that's cooler. So it goes from hot to cold. That's kind of the magic answer. If you're looking for any sort of magic answer and you don't know what the answer is in this class, just say it's hot to cold, because that's pretty much it. So heat travels from a place that is warmer to a place that is cooler. So what we do in air conditioning is we just use that because that's the way nature sets it up, and we create a system that will allow nature to do what it does. We don't create cold, we remove heat. So all that air conditioning is, all that heating is, it's all just the movement of heat. In air conditioning, it's the movement of heat from somewhere that I don't want it to somewhere that I don't care. So in this lab, very simple things, very common things. I've got 5 different water bottles, and actually I think in your lab, does it say you have a 6th one? Okay, so the 6th one, I'm going to put that one here in a minute. I'm going to put it in my freezer, or in my cooler, or in my fridge, and I have to go and measure that one, and I'll give you the reading off of that one. Normally I'd have a cooler right beside of me, but I don't this time. So I'm going to set that one somewhere colder here in a minute. So what do you notice about these right off the bat? So it says bottle 1 needs to be what? Warmer than room temperature. So this is bottle 1. Yes. So what I'm going to do is I'm going to give you the readings. You all are going to walk me through the lab and tell me what's next. I'm going to give you the readings. You're going to record them, and then you all are going to try to work through this data. I need somebody to keep time for me. So if somebody's got a stopwatch, because we got to have like 5-minute increments between, or keep track of our increments between, so we can record our time. What does it ask you first? The very first thing it asks. Okay, so the time is what? Somebody give me a time.
11:15.
Okay, 11:15 here. Y'all are doing this online. Record your starting time, whatever that is. Bottle 1 to start with is 97.3 degrees. So just say 97.3 degrees. And we'll try to keep the decimals, keep as accurate as we can. Bottle number 2 is supposed to be what? Maybe slightly warmer than, or no, it's supposed to be room temperature?
Yeah.
Okay, so bottle 1 is room temperature, and it is 73.9. Bottle 3, slightly cooler than room temperature, and it is 69.4 degrees. Let me do that again. Let me see here. 68.4. The other one is directly out of the cooler or the fridge. And it is 54.9. And the last one is frozen, or out of the freezer. Now this one's been out for a few more minutes than I would have liked, just from setting up, so it's going to be a little different, but 32.2 degrees. And the last one is supposed to be placed into a colder place. So it's at room temperature when it starts. So it is 73.9 as well. So that's your starting on that one. So I'm going to go place it in the cooler. and I'll try to give you a temperature of the cooler, but let's just, at this point, we can say it's around 40 degrees, but I'll see if I can get a more accurate measurement. And also, I'm going to ask you ambient temp somewhere in there, so I'll get the thermometer. So start your timer at this point. So it says wait 5 minutes.
Yeah.
So somebody start a timer, keep a stopwatch for 5 minutes, and we'll take another reading in 5.
Must really be related to bowling. Bowling likes to talk stuff. Y'all cousins or? Yeah. Jeremiah, we call him Bo.
Oh, yeah. Oh, yeah, they do call him Bo. Yeah, he's a something like that.
Last one day when I found out his name was Jeremiah Bowen, I said, where in the world is Bo come from? It's just my last name, or we just instead of Bowen, we just back off of Bo. So we have Bo.
He lost a lot of weight
Yeah.
compared to what he meant. How big he was before.
I think he likes the new job, it's just a little stressful.
So he makes pretty good. Pretty good. Decent, man. Barbell. Very consistent. During the summer, I average like 8 to 1,000, almost 1,000 a week. But in the summer, in the winter, I'm on 100 or 200. Get sometimes drop.
We'll be still recording or something. So the hose for 8 years, I haven't had a hose. I got lucky. Got up 4 o'clock every day. I'm gonna take this class. We close it now, but we don't get out there for that. For 8 years, I worked a 74 shift and we do drive. So now I got to weekend and night. That's what you're gonna do right now.
And this is still recording, so you all are, it may be picking you all up, I don't know.
That's what it said.
I'm gonna do this a little different. We're gonna try this and see, because that way I can have it all here together. I put this in ice water. So this one was room temp, and now I'm putting it in ice water bath. See what happens. Just kind of curious on that one. So how far are we on time?
Yeah.
A minute? 40-30. Okay. And if you're watching this, you can fast forward this part until you get to the next, but I'm not going to cut away and keep coming back. So ambient temperature. Didn't get a thermometer. I'm gonna say it's right around 73. Yeah, it seems like everything's kind of reading 72, so we'll call it 72. So once that timer goes off, our next instructions. Okay, so what you're going to do when you get home, you're going to want to get some graph paper, some grid paper. Pick that up when you're out as well, when you get your supplies. I've never done this way, but I'm actually curious to see how it turns out. I've always wanted to do it this way. So get you some grid paper, and you're going to plot these temperatures in relation to time. So every 5 minutes, you're going to put another plot for each bottle. Coloring pencils, different colors for different bottles. Let me know when we're ready. Record the ambient temperature around each bottle. So each one with the exception of this one. So if this is ice water, let's just go ahead and say this is 32 degrees for what it's in. So okay, we're good. So wait 5 minutes, record the readings. The time is now what? So record your time. 11:22 here. So 4 or 5 minutes later, if you're a little later than that, that's fine. It's all compared to time. So bottle number 1 is the warm bottle. And at this point, what was our starting temp?
97.
All right, at this point, I'm reading 95.0. Number 2, what was room temp? 73.8. Third one was a little bit cooler than room temp, is 69.8. Fourth one, 56.5. And the last one, 30, still 32.8. Still pretty much 32. I would tell you this one's not going to change a whole lot, even if it does. I'm going to tell you it's going to stay at about 32 because it's frozen. And then the last one, I'm going to try to do it at the top, see how that works. $68.2. Now, the one thing that's going to vary with this versus keeping it in a cooler at consistent temperature is that this water is going to get warmer. The ice is going to melt. So the ambient around that one is actually changing a little bit. So it's going to throw us off a little bit. But for this experiment, it'll do what I need it to do. So now you're going to start your time again. So you got a 5 minute wait. While you're doing the 5 minute wait, you're going to do your next thing. So it says record any observations about the appearance, temperatures of the bottles. Is there any way we can do that in a few minutes? Okay. Okay, I'm trying to record. Awesome, thank you. All right, so while we're waiting on our 5 minutes or however long we're waiting,
Water bottle down.
we're doing lab heat transfer. That's Rick, ladies and gentlemen.
You did unlock them. You did?
Yeah.
What time did you unlock?
7:30. I opened at 7:30.
I think we want to make some deals. Are we? Yeah, we're making some.
Oh, okay. I didn't know. I didn't see that.
Yeah, I put them unlock at 7:30.
Okay, that's fine. I didn't know if you were going to be in there. All right, so so it says calculate the delta T for each bottle. Does anybody know what delta T means? It's temperature change. So it's a change in temperature from one time to another. So at this point, we're going to calculate from the starting to after the 5 minutes. How much did the temperature change? So you're going to go down through each one of those and say bottle 1 changed this many degrees, bottle 2 changed that many. So bottle 1, how many degrees did it change? 2.3. Bottle 2. We are outside, so we got noise. We got Rick on the yard. We got motorcycles. 0.1. It was room temp. Bottle 2, bottle 3. If you need to get a calculator, that's fine.
Another 1.4.
That 1.4. Bottle 4. You can get your phones out, get your calculators out. Same math class. It may seem like it by the time we get done. But what'd you get for 4?
1.6.
1.6. 5. Really basically 0. For all intents and purposes, let's just keep 5 will remain at 0 difference the whole time. It's going to stay at 32. Even if I get a little different reading, we're going to keep that at 32. And bottle 6. It started out at 73.9. How much? 5.7. Okay. All right. So calculate the change in temperature in degrees per minute. So how many minutes do we run it? 5. If you all ran it a different amount of time, then your number will be different. So ours, we ran it 5 minutes. Try to keep on the 5-minute thing. But if you ran over by 6 minutes, record the time that you let it run. So bottle 1, degrees per minute. So this is where you're going to have to do some math. So you're going to do your temperature change, which is your delta, the number you just found. Divide that by 5 minutes. So it's going to be a small number. It's going to be a decimal most likely. It's by 5. Yeah. So if the first one, for example, was, what was your delta for the first one? 2.3. 2.3 divided by 5. All right, so you got 0.46 degrees per minute. That's how you'd want to write that out. That's your change per minute. I'm going to try to start keeping time. How much time we got left there for a 5?
10 seconds.
10 seconds. All right, we're getting ready to run through the next one. So take the readings again. We're going to do the same thing. So what we're doing is in 5-minute intervals, we're recording these temps, and then we're going to plot those on a graph. So go down to number 7. Record the temperatures again. So here we go. 91.4 on number 1. 73.4 number 2. 69.8. 59.9. 32.2. And 67.3. The last one may not exactly act like I want it to. It's a little bit different than we normally do it, but I think it'll still show us something. So you're doing it again now. Calculate your deltas. Now, this says calculate your delta of each bottle from step 2 to step 6. So what that means is, it should be step 7. How much did it change from this 5-minute interval to the last 5-minute interval? So what we're going to be doing is we're going to plotting a change every 5 minutes, not a change from the beginning. Now at the end, we'll change it. We'll do a change from the beginning. But for right now, we're just doing it for this 5 minutes. So what you'll probably see is that the rates that these things change when you calculate your degrees per second or degrees per minute, those degrees per minute are going to start to change as things start to equalize. That's what we're looking for.
So are you doing it from step 3 to step 7 on this one?
Yeah, I think those are old numbers. So yeah, I guess it's step Yeah, step 3 to step 7. Sorry, step 3 to step 7. It says step 2 to step 6, but I added something in there. And I've got my 5-minute clock going, so you can back me up, but we should be good to go. And if you're killing time here and you can look at observations, you'll notice that some of these look different than others. If you want to come up and walk around one at a time, you can do that. If you're at home, you'll notice that number 1 is we got a lot of water starting to some condensation starting to build. You can see it's like all over that, dripping off of it. The paper towel is completely wet. This one has some condensation on it. The paper towel is just a little bit damp. This one is crystal clear. Crystal clear. This one has actually got moisture inside the bottle, which is interesting. On the outside, on the inside. And this one's a little bit of a wild card because it's in water. It's not really doing anything, but it might act different if it were in a cooler. But for now, we're going to just go with that. So now it says calculate it again, and then it says take a 15-minute break once you reach this point. We may just do 10 for the sake of time. So this is normally when I tell them to go get a snack or into the bathroom or whatever, and just kind of give it some time. And we may just do it at 5 because I think it'll still show what we want. So I'm counting to 5. We may just stick with 5. We'll see what they do at 5. If we need to do it another time, we can. So feel free to come up here and look at these. Like I said, just kind of one at a time or rotate through, whatever. But interesting things are happening. Notice moisture that's collected on them more than anything. So not only change in temperature, but also change in how much moisture is being attracted to each one of them. "53 seconds till the 5-minute mark. We're supposed to run this 15 minutes, but we'll take a reading at 5 and see. And if we need to, we may even come over and make one at 10 and just come beside it or something, depending on if I think we need to do it again. So you calculate the change in temperature in degrees per minute again. Did that rate change at all? Any of them? On number 9 part, the second part on number 9. So you calculate your delta, and then you calculate your rate. So did y'all get that rate again? Yeah. Get change a little bit on some of them, maybe. All right, so we'll go through and read these readings again, and then we'll talk about what those numbers are meaning. So bottle number, so this will be your number 11. Number 11, when you return, record the readings again. Like I said, it's supposed to be 15 minutes. We're going to try it at 5 and see what we get. 88.5. Number 1. Number 2, 73.9. And this isn't exactly a controlled environment out here either. You know, we could have, the temperature could be getting warmer, so it's 70.5. Number 3. Number 4, 61.3. The last one is still 32.2. And, well, the last one, not the last one, next to the last one. And number 6 is 68.9. So that one, like I said, I think that water is changing temperatures enough that it's not reacting quite as much. So that one's probably an outlier. We may not even use that one too much, but you'll still see what it's doing and how it's working. All right, so number 11 says to do that. Then you plot those temperature on a graph. So if you're doing this on your, you're working through your graph, you'll come back and you'll record number 11, all those readings. Those are your values. So the thing you're recording on the graph is the actual temperatures at each time. You're not recording the rate at this point. You're just recording the temperatures. So you're just saying that, at this 5-minute interval. So on your x-axis on the bottom of your graph, it's going to be, 1, 2, 3, 4, 5, or 5, 10, 15, 20, 25, however long, however you want to do that. Minutes. That's your minutes. So that's your, independent variable. That's the thing that doesn't change. So we just have 5-minute intervals. And then on your y-axis, that's where your degrees is going to be. So you're just going to run over 5 minutes, run it up to how many degrees it was when it started, and then record it at 10 minutes or whatever, so on and so forth until you've recorded. Then you could connect those all with a line, color code those, so we can see bottle 1. This is the trend that it followed. Bottle 2. This is the trend it followed. So I think it'll give you a real good visual representation of what's actually going on. I'm going to run this for another 5 minutes since I'm already starting it anyway. And so you'll have more readings. That way you can have more of a curve if you have more readings. So over beside number, let's see here. Beside number 11, you may want to make another line and say, after 10 minutes. So that was after 5 more minutes. This would be after five more minutes after that. So we're just going to take another set of readings. So you'll just record those, the next step. So this would essentially be like number 15 if I had put this in there. We were supposed to wait 15 minutes before we took this reading, but I'm just going to take it every 5, if that makes sense. Still got a lot of sweat, a lot of moisture on number 5. Number 4, the paper towel's getting pretty wet at this point. The bottle is pretty wet. Number 3 and number 2 don't have anything. Number 1, you still got a lot of condensation inside of the bottle on that one, but there's nothing on the outside. And then this last one's just sort of doing its thing. But you also notice there's a lot of sweat on the side of that jar. So kind of figure out what's going on there as well. So what do you think this is? What do you think I'm trying to symbolize with this?
The model is trying to adapt to temperature.
Yes. So if you've watched some of those PowerPoints, you'll see me say, or some of those lectures, you'll hear me say that nature hates imbalance. Everything in nature tries to equalize. So if pressures are unequal, they try to balance. If temperatures are unequal, they try to balance. So what we're doing is we're trying to create a system that creates imbalance so we can move heat where we want it. But naturally, it doesn't want to work that way. Naturally, it moves from hot to cold. And then once it's equal, even if you have the best built house ever, you insulate a house with the best insulation you can get, you've got, the best windows, the best doors, without some sort of mechanical cooling or heating, you're not going to be able to keep that at the temperature you want it, because eventually it's all going to equalize, even if it's built really well. All that insulation does is slows down that process. So, if I have R32 insulation, it just means that that's a longer time for that heat to get from outside to inside, or in the flip side, in the wintertime, from inside to outside. So house heat trying to travel, it's trying to travel from hot to cold, from a warmer place to a cooler place. In the summertime, what's the heat trying to do? What are we trying to fight? Like if I got a house, I'm trying to keep it 73 and it's 95 outside. Okay, the hot air is trying to get in, right? It's trying to attack it. So that's what's happening here to these colder bottles, is that heat is going to those bottles. And it's visual by moisture. You can see that moisture is attracted to it too. So by conditioning a space, we're not only removing the temperature or trying to cool the temperature, we're also trying to condition it by removing some of the moisture, some of the humidity, because that makes the place uncomfortable when it's real humid. So that's actually a good representation of the heat that we're picking up, because the moisture comes with it. So we're trying to fight the incoming or heat gain coming into a house. So when we size a system, we do a heat load duct design class later on, and you'll do what we call a heat load, which is basically taking all the materials in a house and saying, how fast will the heat in this area come into this house every hour? And then we have to size our system to match that heat input. So if the house is gaining 12,000 BTUs every hour, I have to have a system that's capable of removing 12,000 BTUs an hour. So it can pick it up, dump it out. All right, 5 minutes. So beside that, number 11, just make you another column. This will give us another point on our graph, just to help us see it a little better. You don't have to run through all the deltas and stuff on that one, unless you just want to. But we're just going to get some more temperature readings here since we're still got them set up. Number 1, 86.9. Number 2, 73.2. Number 3, 70.0. 70.3 actually. Number 4, 62.2. Number 5, still 32.2. And number 6, 66.4. All right, so I'm going to set it again because we may get another reading. I'm going to go ahead and talk, and then we may take another reading, and we'll just put it down over to the side or something. So the more readings you have, the more better able you're going to be able to see that curve. So if that heat is being attracted to this bottle because it's colder, what's going to happen to the temperature of the water in the bottle as a result? It's going to equalize, right? So if I if I pull this one out of the cooler, out of the fridge, I set it on the table, it's going to sweat, and if I come back in 2 or 3 hours, chances are it's going to be room temperature, right? These that are room temperature, I could have put them in the fridge a couple days ago, pulled them out, let them sit, and now they're back to being room temperature. If I set it in my truck, what's going to happen? On a hot day, it's going to get hotter, right? So in the wintertime, what's trying to happen in our houses? Hot air is trying to get out, right? Now, what you're going to find through this lab, which ones are gaining the most temperature? Like number 1 and number 4. What are your deltas on those? And your rates? Number 1 was changing quicker. Okay, so what was the original temperature difference in number 1 versus the outdoor temp? So it was 90. Okay, and outside is 72. We said. All right, so you got a 24 degree delta from outside. That difference between outside and your bottle. What about number 4? What was it to start with? 54.9. What is it now?
10 minutes.
Yeah. Right now it's
62.
60. Yeah, it's still 62 point something, 62.2. So it's getting warmer. This one's getting cooler. Which one's raised the most?
The bottom one.
Huh?
The bottom one.
Which one has changed the most? Sorry. Which one has the higher delta? Number one. So that's interesting because they were both about the same amount of degrees from the outdoor temp. So this one was about 20-some degrees below. This one was about 20-some degrees above.
I got 2.9
For your rate.
Yeah, that's what.
Okay. See, I think that's interesting. And that's something I've always kind of wondered, but I never had it set up to where they were about the same degrees apart. But this one was about the same distance from outdoor as this one was, just in the opposite direction. So this one's cooling down. This one's heating up.
What does the
But this one seems to be cooling down a whole lot faster than this one seems to be heating up.
the wind have a lot to do with
Wind could have quite a bit to do with it because we're outside. That could definitely.
it? It's cooler right here.
Yes. Yeah. If I put it in the sun, it'd heat up like crazy. These would. And this one would slow down its cooling because it's getting, what kind of heat are we getting? Okay, here we go. What kind of heat transfer is happening right now? We're in the shade. We're standing out in the building, but right over here is the sun. So what's happening where I'm standing? We got wind blowing,
Well, that's being heated up.
convection. Probably getting a little bit of radiation from over there, but it's mainly all convection in the shade. But as soon as I step over here in the sun, now I pick up another kind. So now I'm still getting all the convection. I'm getting the wind, but now I'm also getting that. So it's like a whole different thing, whole different kind of heat. So that concrete is going to be a lot warmer because it's getting radiation and it's getting the convection that's in the air. That's actually a really cool analogy I've never been able to do inside. So 107, we'll take these one more time since we're that close. I'm gonna go ahead and read them. Do them. Number one, 85.3. Number two, 73.2. Number three, 71.1. Number four, 62.8. Number five is still 32.2. And the last one, for what it's worth, is 64.0.
Now, if you went to put bottle 5 out in the sun, it would cool down a lot.
Yeah, it would.
A lot.
It would warm up a lot. Yeah, it would get a lot warmer.
Where that one-
And if I were to put one of these room temperature bottles out there, is the temperature any different between here as it is there? Like the temperature of the air?
No.
No. But because I'm getting radiation on it, if I put my thermometer out there, it's going to say that it's warmer because there's two different things acting on it. It's getting convection current. That's the actual temperature. That's why when we say, if possible, when you're measuring ambient temp, measure it in the shade, because that's giving you an accurate reading of what it actually is outside. Because once you stick that probe out in the sun, now you're getting that radiation on it, and it's adding additional heat to it more than what's just outside. So if you got a thermometer and it's sitting out in the sun, or if in people's houses they put their thermostat, they put it right up against close to the window or where the evening sun comes in and hits it, they may have issues with their system. In heating, I've seen people have that trouble to where, they put it to where the evening sun comes down and they keep their windows open. Evening sun hits that and it fools their stat to think it's warmer than it is. And then their furnace don't kick on like they want it to, and they think it gets colder than it should. So just move that stat out of the way. So kind of crazy, but yeah. Putting it in a kitchen close to a stove or something, they get radiant heat off of that. It'll heat that stat up and make it think it's warmer or cooler than it is, warmer than it is. All right, so once you get through that, calculate total delta T. So what does that mean? Calculate the delta from step one all the way to the last reading that you had. So what was the total temperature change?
See what the last reading was.
The last reading you just took. So we took 3 readings, and we kind of added some extra stuff there.
You want to do it from what we just took?
Do it from the one you just took. Yeah, the last reading. So the very first first reading of each bottle. So for number 1, let's use an example on that one. Number 1 was 97.3, and it is now 85.3. So it's So it has it's changed 12 degrees. So that's its delta. Its total delta. And then what you're going to do is you're going to calculate your total change per minute, your total rate, which is, let's see, 5, 10, 15 more, 25 minutes. Is that right? Let's see. What time is it? What time did we start? 11:15, and it's 11:51 now. It was about 11:49 or something. So let's see, 11:50. So we ran these about 25 minutes. No wait, 35 minutes. Is that right? We started at 11:15. You said? Okay.
That's what.
Probably had a little dead time between before I reset my clock.
So we'll divide.
So the total time, use your total clock time. So even though we did some intervals, we had some gaps in there because we stopped our clock and then we done our measurements. So 35 minutes is your total time. So do that temperature change on each one over a 35-minute time interval. So for example, and this is on number, and I know this gets confusing, that's why I'll walk you through it. Calculate the change in temperature in degrees per minute. So for bottle number 1, what was its delta? 12, you said?
12.
And divide that by 35 minutes. So its total rate of change was 0.34 degrees per minute. But when it started, what was the very first time you calculated it? What was its rate? Like a number. .46. So its total rate was 0.34, but its first one was 0.46. Why do you think that's changed? Why do you think that total is a lot less? If you were to calculate all of these rates, which I didn't have you do them, you would have noticed that those rates, as everything gets closer to zero or closer to equal, those rates start to slow down because the rate of exchange slows down the closer they get together. So hot goes to cold at a rate relative to what? Fill in the blank. What do you think? You can say it. It's fine. The big fancy little symbol that we just learned, or little phrase. Hot goes to cold at a rate relative to, delta. Delta T, right? So what does delta mean? Delta means difference, right? So it's temperature difference. So hot goes to cold at a rate relative to the temperature difference. So how does that affect us? Well, the colder something is compared to something else, the faster heat's going to attract to it. So if it's 95 outside and it's 70 in my house, I'm trying to keep it 70, that's a 25-degree delta. Heat's trying to get in really, 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 really fast. What if it's 0 outside and it's 70 in the house? The rate of exchange there is probably going to be a whole lot quicker because now I got a 70-degree delta. I'm trying to fight 0-degree outside air, 75-degree inside air, moving from inside to out. So the bottle on the end, or let's see, bottle number 4 was out of the cooler. So it was attracting pretty quick. The next one had been out of the cooler for a little while. So it's attracting it. It's warming up, but not real fast. Its rate of exchange is not very fast. Why? Because they don't have that far to go to get to equal anyway. So like the more different things are, kind of like people, the more different things are, the more they tend to fight. So that's kind of what these are doing. Nature's fighting with this imbalance, and it's saying, you are extremely different than me. I'm going to destroy you. So that's kind of what's happening. I'm going to make you become equal. So that's what we're trying to fight as HVAC guys. But that's also what we're using to make it do that. So we're making coils warmer, we're making coils colder. And as a result, we can attract heat to those coils because they're warmer or because they're colder. So in our house, we have heat that we don't want. We have heat that we don't want it, somewhere that we don't want it, and we have to take it and send it somewhere that we don't care. So somewhere that we don't want it, inside the house. It's warm, it's hotter than I want it. Somewhere that I don't care, usually outside. So I got an indoor unit and an outdoor unit, or some sort of indoor coil, some sort of outdoor coil. So those coils are full of refrigerant. Not going to dig into that too much right now, but that refrigerant through the process, through the refrigeration circuit, makes that coil colder. As a result of being colder than the air temp, it attracts heat to it. Now, there's also something else that happens in there called evaporation. So that's your evaporator. It evaporates in the coil. The refrigerant does. We'll dig into that on one of your videos. I talk about that quite a bit. But basically, because the coil's colder, now how much colder should it be? So there's where you have to get a little bit specific. Like, I know it should be colder. How much? Well, it depends. It depends on what type of system you're running it. If it's an air conditioning system, or if it's a cooler, or if it's a freezer, if it's a chiller, what's your application? Each application is going to have a little bit different temperature difference. But for residential air conditioning and basic, HVAC, which is just comfort cooling, is what we'll call that. Comfort cooling is where people live, houses, rooms, buildings. Comfort cooling, you're normally going to run that evaporator about, and this is a number you might want to jot down or key, but you'll hear me say it a lot. It's going to be about 30 to 35 degrees cooler than your indoor temp. Now, that doesn't mean that the coil itself, like the surface of it, is colder. We'll get into all that, but that just means when I look at my gauges are going to tell me a pressure. And in one of your videos on refrigerant and gauges, I explain how that works, and it talks about saturation temps. Those saturation temps tell me how cold the refrigerant is inside of that circuit and what its saturation point is. So I want that number to be about 30 to 35 degrees colder than it is inside. Well, what does that mean? Well, on a 75-degree room, I'm going to have about a 40-degree coil temperature. Why would I not want it 30 degrees? If delta means it travels faster, why not have it faster? What's going to happen at 32? Okay, why is it going to freeze? The refrigerant doesn't freeze. Why would you may have had this at your house, your coil freezes up, turns to ice. So condensation, all right, this right here, all right, see all that? That moisture is being attracted to it because I'm conditioning this air. If this were big enough and I could run it long enough and keep it this temperature, I can essentially cool a room with it. That's basically what an air conditioner is. It's one of these big enough to attract enough heat and keep doing it. So we run a system to keep that temp where I want it, to keep the coil in the condition that I want it, so I can continuously do what this is doing, which is attract heat. This has a limited capacity because eventually it's going to equalize. Our air conditioning system can run and keep that coil at that temperature all the time.
Is there any way to draw that moisture where it would go to the
it's going to attract to that coil because it's just hot goes to cold and moisture goes to cold. So we get rid of it, we catch it, it runs down the coil, it goes out of drain. So we run it out of what we call a condensate drain. So that's the purpose of that coil, is for it to catch it. There's some systems that will freeze up, like a freezer, for example. A freezer, it's below zero in those most of the time. So in order for a 0-degree freezer to get colder or to stay cold, what do you think that coil has to be in it, evaporator? I got a freezer that's 0. You don't have to give me a number, but if the evaporator in a house needs to be colder, I'm going to remove heat from a freezer that's 0. You wouldn't think there's any heat in there, but there is. How am I going to keep that freezer? I got to make it colder than 0, right? So that's where a lot of people get in trouble of saying, well, what should my gauges say? What temperature should this be? They want a definite answer. Like every time you look at your gauges, there should be a big green line and a red line that says green is good, red is bad. Like those ones you buy for your car that you fill up your car AC. Keep it in the green and you're good. Well, it's based on pressure and temperature, but they dumb it down so people can buy that and they can sell it to you. So there's not the red and green on your gauges of like, this is good and this is bad. You got to know where that should be. It's going to be different for different refrigerants. It's going to be different for different applications and in different conditions. So if it's warmer in the house, that coil is going to be warmer. If it's warmer outside, Your outdoor coil is going to be a different temperature, a different pressure. So if I'm doing hot goes to cold, that evaporator has to be colder. Now, what about this one over here? This guy on the end. Did he change temperatures?
But one reason it's so high, I think.
Well, yeah, that was just, yeah.
But it did change.
It didn't change. So it didn't absorb any heat. What do you think?
It did absorb heat.
It did absorb heat.
But the ice still in kept the water 32 degrees.
Okay, so the ice kept the water 32, and that's part of what's going on. What if this were a solid block of ice and it wasn't in a bottle? And I was just constantly, if it was melting on the table. And I was just going to say, I'm going to keep this ice on here, and I'm going to measure the ice. The ice will always be 32 degrees until it completely dissolves. The water around it may get warmer, but ice can't get above 32 degrees without melting in our atmosphere. So the bottle's keeping it in. So it's it's a little bit of a different, but like if I had just a block of ice, that ice would always stay 32. So is it absorbing heat? Like if I set a block of ice on this table, would it melt today? Yeah, it would melt. It would melt till it's completely gone. So why did it melt? Because it's absorbing heat, but it didn't change temperatures. These all changed, right? Okay, so until it's fully melted, it wouldn't change, but it is still absorbing heat. It's absorbing heat at a much higher rate than these are. So look at this. If you look at water, and if you can imagine, and it's hard to see, I'm going to show you this. So this is completely like soaking wet. Like I can wring it out. Where'd that water come from? If you say inside the bottle, I'm going to throw it at you.
Condensation on the outside.
Condensation on the outside, right? Well, where was it? It just appeared. It's like humidity. So it's water vapor. So in the air that we're breathing, there's vaporized water droplets that are not liquid, but they can become liquid. Right there, right? They attract to the colder surface. And if I were to say that the water symbolizes heat, which one attracted the most heat? This one attracted quite a bit. But this one attracted way more. All right, so you're going to learn in your lectures that you watch online about something called sensible heat and latent heat. If you haven't already watched that, you're going to watch those. Sensible heat is the heat that we measure with a thermometer. So I always say it makes sense. So these 1, 2, 3, 4, 5, those were all sensibly changing. So I could stick a thermometer on them, I could measure them. This one changes this many degrees. Makes sense, right? If I say how warm did something get or how much heat did it get, odds are I'm going to say that it is that it makes sense. It's sensible. It's gaining temperature. But what about this one? It didn't gain in temperature at all, but it's absorbing heat. So what happened inside of this bottle? This was completely frozen when I started. Now it's starting to become liquid. If I ran it long enough, that would eventually completely thaw. Once it thaws, that ice is no longer in there. Once it thaws, the water can start getting warmer again. So what you'll see on this lab, if you go over to the back, you'll see a thing that looks like that. Sensible heat, latent heat. It's a little chart. And there's some of these in the PowerPoints. I talk about them in the PowerPoints. So notice there at the bottom, the very, very bottom, it talks about temperatures. It goes up to 32. The little line goes up to 32 from below 32. So could you have ice that's colder than 32? Yeah. You could subcool ice to once it's 100% ice, it can become colder. But once it reaches 32, what's it start to do? It starts to melt, right? It starts to become water. But it doesn't just go boop, and become water. It has to go through the process of melting. Why does it go through the process of melting? Because it's absorbing heat, right? It's picking up heat. So once it picks up heat, water can thaw, or ice can thaw it can absorb a rate of 144 BTUs. So it takes 144 BTUs to thaw a pound of water. I think it's a pound. Yeah, yes, pound of water. So this is all from a pound of water. So it starts to talk about BTUs a little bit. Now, once water completely thaws, once this completely thaws, will it start changing temperatures? Yeah. But until it completely thaws, it won't. It will not go through a sensible change and a latent change at the same time. Now, like I said, this water could heat up, but this water, they just happen to be in the same container. It's holding them together. If it was just a block of ice and it was sitting here melting, that water is not going to become 33. Because once it becomes 33, it's already water. So if I put a block of ice in a bucket, I was able to catch it, and I was able to hold it up to where it dripped down into the bucket. So the ice would not get warmer than 32. But it would melt, and then once it melted, once it became 100% water, that water can warm up. So then that's a sensible change. So notice the line that goes up. So right here, that's sensible change. So what's the boiling point of water? Ronnie, what's water boil at? I know.
212.
212, right? 212 Fahrenheit freezes at 32. 100 degrees Celsius, 0 degrees Celsius is freezing. Once it gets to 212, what's it reach? It reaches its boiling point. So at 212, you put water on the stove, you take water out of your faucet, you open it up, put it on the stove, it's going to start to heat up. Well, let's say it's 70 degrees when it starts. What do I have to do first in order to get it to boiling? Huh? Turn the stove on. Okay, I got to turn the stove on. I go buy a stove. Yeah, I have a job. Yeah, a lot of things. Assuming I have a job and I have a stove and I have the ability to turn it on, and I turned it on and I filled it up with water. What's it got to do? It's got to heat up, sensibly or latent? Sensibly. I got to get it from 70 degrees to 212. 71, 72, 73, 74. I'm adding heat, right? It don't take a lot of heat to get it to that point. How much heat does it take to get water from 32 degree water all the way to 212? You look at that chart, see that? It's maybe a little hard to look down at the bottom. So the bottom talks about BTUs, and there's a scale there. So from 32 degree water all the way up to 212 degree water, what's the difference between 32 and 212? 1 BTU will change 1 pound of water, 1 degree Fahrenheit. So it's 1 to 1 to 1. So if I add 1 BTU of heat to this, it'll change it 1 degree. Well, if I got 1 pound of water and I want to change it 180 degrees, I got to add 180 BTUs to it. So it takes 180 BTUs to get 32 degrees of 1 pound of water. So this is about a pound, 16 ounces. Pound of water up to 212. All right, 180 BTUs. That doesn't mean anything to you at this time. A BTU is about the quantity of the amount of heat in a matchstick, kitchen match. You strike that, it's about that much heat, that's a BTU. Kind of give you a little idea of what it is. Once it starts to boil, so you got that water on, everything's getting warm, it's getting hot. Why does most recipes say bring to a boil and then let it boil for 10 minutes and then simmer? Or turn the heat off, remove from heat. Why does it insist that you get it to boiling? So if I take an egg, I'm gonna boil an egg. And I say, I got 211 degree water. And I don't like to boil because it steams and it makes my kitchen all steamy, and I don't want to do all that. So I'm just going to get it good and warm. Will that egg cook very quick? Or maybe, I guess it would eventually cook. But if you tried to cook it in hot water, and you didn't boil it, it's going to take forever if it ever cooks, because it has to get to the boiling point. Now, 211 to 212, that's only 1 degree difference. Doesn't seem like a big deal, right? So once I get to boiling, can I have 213 degree water? What do you think? According to this chart, can I have 213 degree water? As soon as it gets to boiling, it's the same as the ice. As soon as it boils, it starts to change states. Once it starts to change states, latent change is a change of state. Sensible change is a change of temperature. So once it starts to boil, it's still absorbing heat, and actually it's doing it at a much huger rate, much faster rate. About 1,000 times in refrigerant, it's about 1,000 times more heat can be absorbed through the latent change than it ever can through the sensible change. So latent heating is where we do all the work. So inside of our coil, inside of our air conditioner coil, our refrigerant is going through the process of evaporating and condensing. And that evaporation process and that condensing process is what does all the work. I don't expect you to understand all that right now, but if you can understand this and say, I don't know why this guy didn't change temperatures, but boy, he sure did a lot of work. Look at all that moisture it attracted. Look at all that BTUs it attracted. This one did quite a bit, but not as much. I could have had these both. I could have had this full of 32-degree water and this one full of 32-degree ice, and it would have been about the same. This one would have done some. This one would have done a lot. And they're both the same temperature. But this one has to go through the change of state first. So while it's doing that, it absorbs a whole lot of heat. Imagine if you've got something, you got a cup of hot coffee, and you want to cool it down a little bit. So maybe like in the mornings, I don't like to drink my coffee real hot. So I'll throw a piece of ice in it, just like one piece, just to knock the top off of it. What if I took that same amount of ice and I put cold water in it, poured it in there? Think that's going to be very effective? We could run a test on that. I could take some water and I could put an ice cube in it, and I could take one that has like 32-degree water, and I could dump that same amount of water in it, and it's just not froze. Which one's going to cool the coffee down quicker or more?
Water.
Huh?
The water was 32 degrees.
Think so?
It would do it quicker, I would think.
What's going to happen to that water? It's immediately going to absorb the heat, right? Because all that heat's going to attack it. Well, that ice, because it has the ability to stick around a lot longer, because it's frozen, stay in there more, and it can absorb a lot of heat because it has to change states before it can warm up. So before that hot coffee can attack it and make it the same temperature as coffee, it has to thaw it first. So by doing that, it takes a whole lot more energy from that coffee to attack that, to regulate that. Does that kind of make sense, I guess? Oh, it's kind of confusing. All right, so at the end here, it starts talking about, so it says, what can you observe about each bottle? We've kind of already talked about this, so you can kind of fill that out. Now it says calculating BTUs. Use the guide to calculate how many BTUs have been gained by or lost by each bottle. Let's see here. I tell you what, skip that part for now. I'm afraid we may come back, we may reference that, but don't do 18 right now. I just wanted to talk about BTUs, but I don't think I want to go there. So the review questions 1 through 13, you're going to fill those out kind of on your own. You're going to do that plot. You're going to plot that graph and bring all that with you next time, and that'll be good for your lab. So if you're watching this and you're going to turn this into me, you can bring this in. You could submit it online as far as that goes, but just bring your graph in. You can bring these review questions in, and we'll grade those, and that'll be part of your lab grade. So with that being said, it should finish this up. Any questions before I stop this? I know it's completely obscure at this point, but if you understand this a little bit, I can build off this. So if you just have at least an idea of what's going on, I can do something with that.